So, science or whatever, right?
Yeah. All right.
All right. So, I'm a physics guy, and I'm nowhere near like where you guys are at with like. Are you both in like the graduate level?
Yeah.
Okay. So I only dabbled in graduate level physics. I didn't like take a full on thing. So you guys are like hardcore. What's graduate level science like?
It's a lot of so when I think about graduate level science, it's not so much the classes as much as like the just primary literature.
Okay.
Right?
Gotcha.
So I gotta say the classes, I think my undergraduate classes were harder than my graduate classes. So 100%. Easily, hands down.
Interesting. Yeah. Okay, so graduate's a little easier in some class. Well,
I'd say the classes are easier.
Okay, gotcha.
I'm like teaching myself a ton of shit and and just reading primary literature, like reading like science journals, nature journals. You have to know about your field, you know what I mean?
Yeah, totally. That's crazy. That's cool.
My general knowledge is shrinking, but my specific knowledge is like
just on it. Right. I feel you. All right, cool. That's awesome. So, Sam, you're biochem.
So I did biochem my undergraduate. I'm more of in this area of biophysics.
Oh, cool.
So a little bit closer to you. I work with like free energy calculations, kinetics, equilibrium dynamics, stuff like that.
All right.
What you did with the sheep size. Oh, dude. So I work with the protein system. It's a giant pore that connects two cells.
Okay.
I work with a lens protein.
Mm-hmm.
And so people don't really think about this. Like our lenses, they're living. They're made of living cells.
Okay, your lenses.
All lenses.
All lenses.
Yeah. Because there's no blood vessels in them.
Oh, okay, got you. All right. I thought you were talking about like, okay, got you.
Physical lenses in your eyeball that work as a lens.
Right.
It's coming in and focusing and shit.
Okay, cool.
So those are made of living cells.
Right.
Living cells need things like sugar, metabolites, and oxygen.
Okay, right.
Blood is what delivers all of that.
Right.
But if there's a bunch of blood in our lenses, all the light would scatter and we wouldn't be able to see.
Yeah, our eyes would be like straight red, right?
Yeah.
Like you wouldn't see nothing. You just see red all the time.
If you're looking at someone's eyes, you'll see like veins go like up to the edge of the cornea almost.
Oh yeah.
It's like white. You have like some red little lines go to the cornea, and then it's clear. You just see like the color of the cornea and like just the blackness of the pupil. Like right now, you'd see them extra red because. Right.
Yeah, right. At this book, yeah.
What happens is the blood deposits the metabolites like oxygen, sugar, and other stuff.
Okay.
Deposits it near the cornea and really complex and sophisticated water channels.
Okay.
Bring it in and take it back out.
Really? Okay, so instead of
one of the water channels that does that. So that's why they call it aquaportin, because it's like aqua for water.
That makes sense. Okay, cool.
So our lab works with both aquaportin and connexin.
Wow, that's really cool. All right, awesome. So your lab works with like how you get the living stuff you need to the lens of your eye. Is that what you're...
That's like the biological relevance. What we do is we isolate the protein that does that.
Okay, I see you.
And then we put it on a little graph, that big.
Super small.
Yeah. And you shoot electrons at it. You can take pictures of the protein.
Wow.
In near atomic detail.
Wow.
You reconstruct these proteins.
That's an electron microscope you're using, right?
An electron microscope.
Okay. Cool.
Yeah.
So like how a normal light microscope light microscope, the light gets manipulated. For an electron microscope, the electrons get manipulated and you see at that level what's going on, right?
Yeah, because electrons have the de Broglie wavelength of an electron is like about 0.8 angstroms.
Right. Okay.
That's why you get that resolution.
Right. So, that's a whole other thing too, that electrons even have a wavelength, right? Like, what does that even mean?
Yeah.
Hey, what does that even mean, right?
Lots of mechanics. I mean, really anything with mass.
Yeah, so everything. So like we think of electrons, these little balls just floating around, but like you can think of them as a particle or as a wave. And if you think of them as a wave, it's useful for electron microscopes. Electron microscopes wouldn't work if electrons didn't have wave properties, right?
Yeah. Definitely.
So
measuring phase and amplitude.
That's crazy. So it's not even that we have evidence that things are a particle and wave, but we're using it to our advantage already with electron microscopes and all that stuff. That's so cool.
Yeah.
All right.
Yeah. They've tried to measure, like, see with like some quantum experiment to see how big an object can get before it starts behaving as one thing or the other.
Before it like collapses the wave function and like figures out what.
Normally it's for like the smaller particles, electrons, and photons. But I think proton is like that's the cusp. That's the cusp. I'm pretty sure proton is near the cusp.
Proton. Okay.
So you know what quantum tunneling is, right?
Dude, quantum tunneling's out of control.
But you're right. So you probably have a better understanding than I do.
Like, fuck, man. So with quantum mechanics, it's like I could say all the things that quantum mechanics says. Like I could say that out loud out of my mouth, and you'll hear it. But like I don't. It doesn't make any sense. It doesn't make any sense. You know what I mean?
Yeah, it's stupid.
Yeah, it's the stupidest shit ever. Like, who came up with that? Like, it doesn't. All right. Well, yeah. So like quantum tunneling is the whole thing where you have like it's an energy well, right? Where like you would expect the electron to sit, right? But like with quantum tunneling, what happens is it could get over a hump that it wouldn't normally be able to get over. It could get over that energy hump and just be on the other side of it somehow. You know what I mean?
It's pretty much the workaround to make sure that nothing moves faster than the speed of light because it's instantaneous and therefore faster. But then they're like, no, it's not faster. It just teleports.
It's not okay, right? That's like right.
That's kind of like what quantum tunneling is.
Yeah.
It's like eventually everything will get over the energy hump. That's just thermodynamic equilibrium, right?
Right.
But like, at the rate that it happens is so slow, it shouldn't happen.
Right.
It shouldn't happen as fast as it does. So now the explanation is it's tunneling through. Tunneling.
That's crazy.
So that happens in our stomachs.
Of what? Okay, that's all right. So how is that happening in our stomachs? Teleportation. Explain to me how teleportation is happening in our stomachs.
There's this enzyme, and it's called chymotrypsin. There's also an enzyme called trypsin. Now, enzymes, they're just giant molecules that like cut up proteins and digest proteins.
Okay.
Right. Sorry, enzymes just lower the activation energy.
Right. That would.
Chymotrypsin just cut up proteins.
Right. So okay. So to review, it was like enzymes that cut up proteins, but like they help proteins get cut up how they normally would anyway. It just makes it faster, right?
Absolutely.
Yeah. Okay. Cool.
So there's in the mechanism. There's a hydride transfer or a proton transfer, not a hydride transfer.
Okay. Protons. Yeah.
So it's a proton transfer between the side chain serine and the carbonyl carbon of the peptide backbone.
Oh boy!
And that proton transfer is a quantum tunnel.
So quantum tunneling is happening in order to make that happen. Like that's a fact.
In order to digest your food. Yep.
Yeah. Okay. So to recap, that's how teleportation is happening in our stomachs all the time.
Yes.
Just I just had to say that one more time. I just had to put that out there. That's out of control. Okay. So that's what Sam does. So Jay, Sirius Jay, what do you do? What are you doing? What are you up to? What's going on?
I'm basically trying to study the degradation products of terpenes.
All right. Degradation products, like, so terpenes are breaking down, and you're studying what they break down into, I guess, right?
Yeah. See if they make any toxic things. We're also trying to figure out like what mechanism they degrade by.
Okay.
Seeing some interesting results, and this is for vaporizing weed. You know what I mean?
Yeah. Okay.
I'm like dabbing
So you're dabbing for science.
Dabbing for science, yeah.
All right, cool.
I think I've done the first quantitative dab.
You've done That's amazing, dude. You're going down in the history books for that. The first quantitative dab. So, okay, so if you had to explain, what were they, terpenes?
Mm-hmm.
If you had to explain what a terpene was to a 5-year-old.
Okay, so terpene is just this. It's a chemical that like kind of oily, light oil.
Okay.
And very smelly. It's just volatile.
What does it smell like?
There's tons of them. So like
they make odors easy, I guess.
Yeah, they are odors.
They are odors.
They are, yeah.
Okay, so that's where our nose picks up. Like when we smell shit, it's always terpenes.
Yeah, so like think of like a lemon or an orange, right? I mean, there's a lot of chemicals, but like most terpenes are the aromatic compounds. So you think of like a lemon. Lemon has in its rind, it's got limonene.
Okay.
Little molecule that is the hydrocarbon, so it's the same atoms in it that like gasoline has in it, basically.
Gotcha. And, wait, so lemons have the same thing that gasoline has? It's really simple. It's the same thing.
Yeah, I mean everything's made up of atoms.
Well, yeah, all right, that's true.
We're all stardust. Yeah.
Oh man, that's a whole other thing. But yeah, okay, so everything's made up of atoms, but like the same type of atoms are coming out of lemons as are coming out of gasoline.
Yeah, I guess that was a bad example. But if you think of kerosene or something, right? Like it's just a hydrocarbon. And so they're all the hydrocarbons.
Now, a hydrocarbon is when a hydrogen and a carbon are chilling together.
Yeah.
Okay.
Yeah. So like tons of things are hydrocarbon. Like cellulose is a hydrocarbon.
Okay.
No, starch. Starch. That's a hydrocarbon. Yeah, it's a hydrocarbon. And so,
like anything organic would be a hydrocarbon, isn't it?
Well, a lot of things. Depending if they have nitrogen groups in them, then they start being, if the molecule is almost entirely carbon and hydrogen, it's a hydrocarbon. But I mean, if you start adding other types of groups onto there, that
gotcha.
It starts not being a hydrocarbon.
Okay.
Yeah.
All right. I need to pause for a second. And everything is chemistry. Everything is chemistry. You can explain it all like these crazy ways, and it's crazy. Like everything that makes up everything that we experience every day is chemistry. That's crazy. That's out of control. So, so these hydrocarbons, they're the ones that you're looking at in particular make smells.
Yeah. Okay. So think of a few things in lemons and oranges, just limonene, right? Like, and it's also in weed too, limonene. And
interesting.
There's stuff called caryophyllene it's also in black pepper.
Okay.
Myrcene, that's actually the main terpene that's in cannabis. Apparently it's also in mangoes, but I honestly don't smell the similarity at all.
It's interesting. Okay, so you're seeing how these things break down and what the pieces are and if those pieces are like toxic or not.
Yeah, and it has implications for people that are
for like vaporizing and stuff like that, right?
Oh yeah, for vaporizing and for just that's basically. I mean, also people that are manufacturing oils and stuff like that.
Okay.
Sometimes to high temperatures, and so they might want to modify their production process if they're. I mean, that's something that people already suspect, and it's also for vaporizing too.
Mm-hmm.
A lot of people kind of consider it more of a matter of taste. It's toxic. I mean, they probably suspect it, but it is just like smoking. Like, smoking is bad, and everyone. But
yeah. Nice.
For the kind of unexpected thing is what people are seeing with vaporizing e-liquids is that you're getting like more kind of formaldehyde and
what kind of liquids?
E-liquids.
Oh, the e-liquids, like in the e-cigarettes and stuff like that.
Yeah.
So formaldehyde's coming out of the vapor of e-cigarettes.
Yeah, and it's actually coming out at like higher levels than cigarettes.
Oh shit. Okay.
So cigarettes have a lot of other different very carcinogenic things. Like it was kind of people didn't really suspect, when they first came out with these cigarettes. I remember like the word on the street sort of thing, like what people were saying.
Yeah.
Not officially, but just was that it was just water vapor. It's just like making water vapor. You think of what a load of bullshit.
Yeah, right. So it's definitely not that. It's not nicotine water vapor. There's other shit coming out of there, and there's other shit it's made of.
It's glycerol that's going into it. Yeah, glycerol, propylene glycol.
Glycerol, right? Okay. What's so like? What if you had to? What is glycerol and what is propylene glycol? If you had to explain it, other than that.
Glycerol. All right. Yes. You start with where it comes from is a fatty acid. So glycerol it's almost like it's a type of hydrocarbon, but it has these functional groups on it called hydroxyls, alcohol groups.
Okay, gotcha.
It's three carbon, 3 hydroxy. Yeah, 3 carbons and 3 hydroxys. And so because of how many hydrogen bonds it can make, hydrogen bonds. So quick thing. Covalent bonds, ionic bonds. Ionic are very weak, and they're electron sharing.
Right. That's how the salt is made up of, and like that's why it dissolves so easy in water.
Yes.
Right.
Yes.
Because you can separate.
Covalent bonds are like electron stealing.
Okay.
It's really strong bonds.
Yeah.
Actually, I had that backwards. Anyway, yeah. So covalent bonds are much stronger.
Okay.
They're electron. They're equally shared.
Right. So the covalent bonds are like they're connected because like they're
broken, but
right. They're not. So with ionic bonds, they're sharing an electron.
No, that's like an ionic bond is like hydrofluoric acid. That's
okay.
It's like table salt. It's basically just an electrostatic attraction.
Oh, yeah. Okay. Gotcha. You have a positive and negative. But for the other ones, like you got like it's more complicated than a culomic. Right. Okay.
So hydrogen bond, it's a dipole-dipole interaction. So it's like in between an ionic bond. It's actually weaker than an ionic bond. It's strong enough to be called a bond.
Okay.
So water can make 4, and water has these really intense properties. There's high surface tension.
Right.
So glycerol, due to its high molecular weight, like the carbons in it, and the fact that it can make a ton of hydrogen bonds, it's very viscous.
Okay. So it's like how is it compared to like honey? Is it more or less viscous than honey?
More pourable than honey.
Okay.
But not that much. Yeah.
Okay.
It's really sticky, and it's in you've heard of it. So it comes from fat. So triglyceride that's how fat your body's 3 hydrocarbons.
Right.
Yeah, it's just three fat molecules that they're making.
That would make sense, like because it's triglycerides, 3 fat. Okay.
So, when you make soap, what you take like a fat, an animal fat or olive oil, and you put lime and sodium hydroxide, and then you cut those bonds, and then you can actually separate the glycerin.
Right.
From the fat, and so first people when they make soap, it was just from the fat and the lye, and then separate glycerol. And at some point in like the turn of the 20th century, before that, probably in the 18th century, they discovered some method of separating the glycerol from that in the soap production process.
Okay.
And now they have this glycerol they can just have.
Wow. Okay. Gotcha.
And that's what dynamite is trinitroglycerin.
Trinitroglycerin. 3 nitrogenated glycerins. Yeah. Okay.
It's a nitrogen with a double bond to an oxygen.
Okay.
Double bond to the other one. It's just really electron.
Okay, so we have triglycerides, like that's like the fatty stuff that we have in our body, right? So So now trinitroglycerides. As soon as you put the nitrogen in there, now it's dynamite.
Yeah, nitroglycerin. So it's like you have it's like a connector, like a three-way connector.
Okay.
And your body has fats on the connections, and then they just like cut it, and then they just get the glycerin, and then they put the nitros on it.
Gotcha.
Also, the glycerin is it's like completely safe. You know what I mean? Like they use it as a humectant. Like you can taste sweet, so that's why great. That's why you use them for the vapes.
Totally. Right. And I think that's why like people have a misunderstanding about chemistry sometimes. It's because like they hear something that's bad that's in one thing, but it's completely fine and totally good in the other thing, but they don't really understand how like the chemistry works to make it different in one thing or another,
I think a fun example is sodium chloride.
Right.
If you ate a chunk of sodium, you'd blow up.
Yeah.
If you inhale chlorine gas, you'd suffocate.
That's real bad. But we just put salt on everything.
When you have sodium chloride, the molecule, you literally can't live without it. It's essential to our your way with sodium potassium pump. Yeah.
That's awesome. Chloride. You're absolutely right, though.
Yeah.
Man.
Like those the components of table salt are extremely dangerous. Yeah.
That's crazy. That makes a lot of sense, though. That's really cool. Fucking. All right, I had a thought about something else that Sirius was saying before about the soap. Okay, so like we could do crazy science to soap. We totally understand chemically what's going on to make soap, right? But humans probably discovered soap way before we understood the chemistry of soap, right?
Probably.
Like historically, right? So it's crazy that like we had this thing and we used it, right? What do you think, right? We probably discovered soap when we were back in like, I don't know what age exactly, but like when like just animal fat would drip onto like the coals of the wood or whatever. That was probably the first soap, right?
Yeah, that's where the lye would come from, just like ashes and stuff.
Right. And they probably rubbed that on them because they realized that they hunt better or something, right?
And the consistency changed, and then it's just
but like we didn't really understand what was going on until way later when we could actually explain it with chemistry. Like chemistry is just a better method we have to explain what's going on with soap than whatever we had before chemistry. I guess alchemy, right?
Yeah.
That's crazy too. How like it used like chemistry came out of like a mythical thing like alchemy, where we weren't using evidence to like we kind of, you know what I mean?
Yeah, all branches of science were though chemistry, astrology.
Right. Yeah. And like it's crazy that like these things are still around, but like we have a better way now than astrology but that was all they had back in the past.
There's more. There's astrology. There's alchemy.
I know like homeopathy is an old way to heal people by just diluting things, and like it's bullshit, but it's still around. Like you go to the health food store and you could go to a homeopathy section still, even though it's like old, like debunked stuff.
Our explanations of things have gotten, taken a really kind of long, wild journey.
Yeah, right. Exactly. It's crazy because like we only go by the best way we could explain it at the time, right? So like when we were cavemen or whatever, the best way we could explain it was, I don't know, you put together these two things and like it happens. Like so it's like magical,
Well, or about, like the Greeks already knew about like atoms, basically.
Yeah. So the Greeks thought everything was a mixture of like earth, air, fire, and water. Like everything was a mixture of those four things, and that's why we call different atoms elements, because it's like mixtures of those like core elements, like the fundamental elements or whatever, right? But now we have a better way to explain it. Like we understand that like we have oxygen and nitrogen and hydrogen. Like these are the elements, not earth and water and air and fire.
Even though like it seems when that it's like a more primitive way of understanding it, they could make some crazy stuff.
It's It's true
about how Greek fire is like this some kind of substance they had. They used to word that if you put water on it, it would make it burn more.
Wait, so hold on. So you have a Greek fire that when you put water on it, it gets bigger.
That's fire.
What kind of fire is that? An oil fire.
The recipe was kept secret for thousands of years. And
wow.
Like, it is, and it's like this. It's the white whale of incendiary.
That's crazy. Wait, okay, but like we know it. Like we know that it was just an oil fire is what they were doing, but they put water on it and it would.
Because there's probably a mixture of some other stuff, but they had all sorts of understanding of different not only pyrotechnics, but medicines.
Uh-huh.
Different plants. They killed Socrates with hemlock, right? And it was toxic.
Oh shit! I didn't even know that's how Socrates died. That's crazy.
Executed. Being too much of an intellectual badass.
Yeah, Socrates was fucking. He just like went around. He would go up to people and be like, "You know nothing. You don't know anything." He would just go to every person and be like, "Hey man, you know nothing," and he went to trial for that.
We have a whole a whole definition of like Socratic thinking, or
right?
Learning, you know what I mean?
Is to just like question everybody and everything down to like just until you drive them insane.
Yeah,
that's important though. You have to know like fundamentally why something is, right? Like what's at the bottom, and but like, is science at the bottom? Do you think? Like, is science like the lowest thing that you could question down to? What do you think, Sam?
Are we there yet, or is that the only method? You think science is?
Like,
I don't think that we're at the bottom. I don't think there is a bottom.
Right.
But I think that science is the thing that can get you the deepest.
I agree with that. I like that. I think the deepest in the universe as we experience it, right?
Absolutely. I mean, we can only test what we can experience.
Yeah, right. That's the whole thing.
It takes the science is what like the path that walk on.
Right.
Intuition that guides all the scientists is human intuition. I mean, we're what I mean. We're
totally.
Per se, like think about Einstein, like
right.
People like they have a feeling about something and then they go out
and then they do the process of science to get that feeling to be a reality, essentially.
Because Einstein didn't just deduce the space-time constant, like the theory,
right?
The idea of space general relativity, and just
right.
He didn't it was like doing his math homework, and it was like, oh my god, yeah. He was just like doing constant calculations,
right?
Feeling that there was some kind of dimensionality, joint dimensionality of like space and time. And he's like, whoa,
right, and like that it was interconnected, dude.
Yeah,
yeah, you're right though. Like that's crazy.
And his thought experiments about light and how it moves are should be think about. He has this one thought experiment that proved that light always moves at a constant velocity. This thought experiment says if there's a four-way intersection and you're riding your bike in one direction and there is a car or buggy, I think at the time, coming in one of the from a perpendicular street.
Right.
The car is moving faster than the bike, and since the car is moving faster than the bike, if light, the speed of light does not sum with the speed of view.
Right. Right.
The light of the car should get there before the car gets there.
Right.
So you would think that you're colliding with the car. You freak out, and then the car would drive by.
That's because you would see it.
How can you think the light would be going speed of light plus 50 miles an hour?
Right, exactly. Because when we the way we're used to speed is when we're running or whatever at 10 miles an hour, we throw something at 5, it adds and gets to that. Right. But that's not how light works. Because light has to go the speed of light all the time.
Yeah. Except through different mediums. Right. We can slow it down, you're right. But like the speed limit, like you're talking like in a vacuum, right? So the speed limit is the speed of light. And if you're going 10 miles an hour, you're not going to go the speed of light plus 10. Something's got to give. Yeah. It's 3.8 times 10 to the 6, 10, 8, something like that.
3.8 times 10 to the 8 meters. Yeah, that's it. 3 meters per second. 3.0 times 10 to the 8.
Oh, that's because like 2.98. That's right.
98, right.
It was 3.2. I'm like, I know there's an 8 there. I know there's a 3.
Right. Yeah.
That's it. So we're all scientists here. So Bryce was talking about this other thing the other day. He had this really interesting understanding about light. I never thought about it. So I always knew that it's an electric field and a magnetic field. Something about like the electric field comes out. We were talking about that. Like, how does that? All right. Yeah. So when you should actually know about this is electricity and magnetism.
Yeah, I got you.
So if you have a magnetic field and you move if you accelerate a charged particle
through
a magnetic field, you will create a perpendicular, an orthogonal.
Yeah, this is the right hand rule, dude.
It's the right hand rule. It's right hand rule. So you create an orthogonal electric field. But a magnetic field moving through an electric field creates an opposing orthogonal magnetic field.
Right.
And so you have these orthogonal magnetic and electric waves. That's why it's called the electromagnetic spectrum.
Yeah. Right.
Moving one like this and the other like this.
Right, exactly, because one disturbs the other, and it just makes it go. Yeah.
And that is why light moves at the same speed, because it's self-propagating.
Oh, I didn't even think of it that way. You're right, though. It's
accelerate. It has a constant velocity because of the constant propagation of itself.
That's crazy, dude. I never really thought about why the speed of light was constant, but that makes sense when you think of like the electromagnetic waves like that, like how they always affect each other. There's nothing to. Yeah, like that's how it's propagated forward.
Here's something that I can't understand. I can't wrap my head around. It's light has a constant velocity, right? Speed of light.
Yes.
It doesn't accelerate. It's never off. It's always going that fast.
Right.
If it's there, it's going that fast.
Yeah.
So, let's say you have, like something that is completely opaque and light can't escape.
Okay.
Then like a ball, like a black ball, and you break that ball and light escapes from it. Is the light ever going from 0 to speed of light?
No, it can't accelerate. It's got to be whenever a photon is released, it has to be going that speed. It's never goes from like 0 up to that.
I had a shit example. I was thinking about fluorescence. Like at fluorescence, when the photon leaves, it doesn't accelerate from 0 up to 3 times 10 to the 8.
Right? No.
Just produce.
It just makes like that's the crazy thing about it. It's just so like
velocity. It doesn't accelerate.
So like, dude, if like so like okay, so like when you have the electron rings in the atom, right? If so, the electron doesn't go between the two rings; it instantly teleports down to the other one. And because that's instantaneous and there's no like continuous energy transfer, that's why the photon has to instantaneously be going out at that speed at the same time.
Oh yeah,
does that make sense?
It escapes simultaneous with that, but that's instantaneous.
Right, exactly. So like both things like we wouldn't intuitively expect to instantaneously happen. Like you would think like whenever you see something speeding, it had to get up to that speed, right? But that's not how things work when things are that small, dude. It's crazy. It just doesn't work that way. It's just like, everything that you thought you knew about everything just doesn't work that way.
So what do you guys think about these solar sails?
Solar. So, I don't know. How fast can you make solar sails go?
I heard is that like space travel?
Yeah, it's so like so basically you put up like these big fucking sails, right? Like picture like a sailboat, like a big sail, and you're going through space, and you use like a star's light in order to propel it forward. So that's why it's
exerted by sunlight on large mirrors.
Yeah, right.
Weird.
So it's like because light is transferring energy, right? Like light's hitting you and bouncing off or whatever. Like cities are actually heavier during the day when there's light pushed like bouncing off it than they are at night with no light. Yeah, that's radiation pressure.
Is heavier.
Yeah, right. Because it's I think it's called radiation pressure. I don't want to but when light is bouncing off it, it's actually like. It's like you could think of it as momentum. When you think of light as a particle, it's bouncing off. And
because it's energy. Energy is
right. So that's how these solar sails work. Is like you're actually like hitting light off it, and hopefully, and if it's light enough, it doesn't have that much like inertia or whatever, it'll start going. And these sails will eventually pick it up and just let it go. That's as far as I understand about it.
That's pretty cool.
Yeah, right.
Fast.
Yeah, I don't know how fast dude, honestly, I wish I knew more about solar sails. I got to do more research about what theoretically, how fast they could go, or if we even built one and if it works. I don't really know much about it. I just know the basics.
I think Count Dooku had a solar sail.
Oh, yeah?
When he left the fight with Yoda in Star Wars.
Dude, you know what's crazy? Like, I've only seen the later Star Wars. I've only seen Episode 7 and Episode 3. Those are the only two I've ever seen.
That's interesting.
Isn't that crazy?
You've never seen any of the new ones, then? You haven't seen like 1, 2, 3, 4, 5, or 6.
I didn't see the first one, like the first one 4, right? The first one 4, Episode 4. I didn't see Episode 4, 5, 6, 1 or 2, and then I saw 3. I saw like that 3, and then I saw the most recent one with Ray and Finn or whatever.
Did you see Rogue One? Like you didn't see that one?
I didn't see Rogue One either. No.
Whoa.
Yeah. I'm way behind, dude. I don't know what it is. Like I've never.
For a treat if you ever do get into
it. Okay, I got to check out Star Wars. You're right, but they had solar sails in Star Wars. Is the whole thing.
Yeah.
That's crazy, dude. All right, there's actually another way to get around in space that I was reading about that is crazy. I can't pronounce it though. It starts with an L and it's some French name. It's like the Laguerre Drive or something like that. And dude, this is how it works. It's out of control. So
like some polynomial on one of those things.
Oh, you kind of, yeah. I mean, like that's what I thought of when I saw the name. I'm gonna look it up right now.
What's it called?
So basically, regardless of what it's called, I'll find it. But like theoretically, it could go faster than the speed of light. And let me explain why. Because the way it would work, like, so you know how mass affects space-time or whatever, the whole general relativity thing, when you're more mass, like you're bending space-time. So what they're thinking is, like, so what if we had this thing that could bend space-time in front and expand it in the back, right? So, like, basically, like, then you're moving through you're moving through space-time by contracting it in front of you and expanding it behind you.
Okay.
Does that make sense? I don't know if I'm explaining it good, but so because light, the speed limit of light is, however we said, 3.8, but that light is moving through space, right? So if you can move through space time instead of like, you know what I mean?
You have to rip space time.
I don't even know if you have to rip it though.
It's like a bullet. I mean, a bullet goes through the air and it makes a pressure wave.
Yeah, right. Yeah. So yeah, it's like you're making a pressure wave, I guess, through. That's a good way to think about it, like a pressure wave through space time. I'm gonna look it up right now.
I bet some crazy stuff going on lately. The gravitational waves. Yeah. What was it? It was just like this year that they measured.
Yeah, dude, like that, right? Like that's a whole new way to look at the universe now that we know that gravitational waves exist.
Amazing. They use an experiment was pretty insane.
Yeah,
it was
the LIGO, right? That whole thing.
What?
You talk about the place where they discovered the waves?
Yeah.
Yeah, how'd that work?
It's 2 big tunnels and a cross. Right. And it's really long, somewhere in Italy in the Alps. That's where CERN is too. I think they have like a really strong bedrock around there. I guess from the mountains. I guess. And so these really long tunnels and a cross, and it's an interferometer. And so what it is they have mirrors on each ends of the cross.
Right.
And in the middle, there's a I guess it's like a lens that's kind of sitting diagonal, and so one of the tips of the cross, they shine a laser, and it goes to the middle and diffracts to the 3 other ones, and bounces back. And they have a detector at the beginning,
right?
And so the mirror in the middle is hanging by a thread. Any little disturbance, and there's and then there means something disturbing it, and that they really, that's why it's in this special place in the world where there's no vibrations.
Interesting. And it's in this special place with no vibrations, and it's like deep enough that nothing on the surface even probably affects it, right? Either.
I mean, they said they had some problems, when they were first building it, because it was like trucks rolling around and stuff like that. And there's other stuff going on that they probably have to correct for. And they blank it. Yeah, they blank it. They just run blanks.
Right.
They were finally able to measure. They had to wait. They were waiting for a supernova.
That's crazy.
There was just like a super crazy fucking supernova that was bigger than normal.
Right. And it was big enough that it shook space-time. Like, it shook gravity enough that we could detect it.
Yeah.
That's crazy.
That's silly.
Yeah. Supernovas, dude, are out of control. That's the biggest explosion that could ever happen in our universe, right? That's like the biggest thing is a supernova. That's a star exploding. Like, right?
Like a star bigger than we can't even. It's hard to imagine how big our star is, and this thing is.
So you're right. Like, our star is super average, and this star is super above average, and it's exploding.
Red giants, right? Is that what they're called? No,
red. So our sun will actually become a red giant. Yeah. But when, like, so if it had more mass, that's when you, like, so every star moves up to like red giant, right? But then if you have more mass, then that's when like supernovas happen. But if you don't have enough mass, that's when it burns out and you become like a white dwarf, whatever, and like go burn out.
This is like a hotspot kind of like. Do you know why stars expand or contract?
Yeah, it's called hydro. It's so the name is called hydrostatic pressure. But what it means is like, so the sun is going through like nuclear fusion. It's like plugging atoms together, right? And it's pushing, and that's energy, and it's pushing it out, right? But gravity is pulling all the mass back in. So the stars stay nice and circular because, it's exactly like it's like a knob. And if you have more fusion happening, more mass, right, then you're gonna have a bigger star because like there's more energy being outputted, right? But if you don't have enough, then it's gonna be smaller because gravity's like crunching it in. Right.
But doesn't it also matter how it attracts mass? Because the core starts out big and pushes a lot out, but eventually the core is getting smaller because it's using the iron. It's using the hydrogen, right?
Right.
So it's creating these heavier elements, and so doesn't the core shrink? Or am I getting this wrong?
Well, see, the thing is, like, even though the core shrinks, the amount of mass is still like classically the same, at least, right? Like think of it this way: like if I take a piece of paper and I have some mass and I crumple it up into a smaller thing, I still have the same mass, you know.
I guess I'm trying to figure out when a supernova would occur. Like,
so what happens is when a supernova happens is when you start getting really heavy elements in the middle of the star. So like you start with hydrogen, helium, and then you're making helium, and then helium's fusing, and like all this stuff's fusing. And when you have a really massive star, super massive, like there's enough temperature and pressure to be making like really heavy elements, right? And I think it gets to a certain limit. I forgot what element it was, but like it can't, like there's not a fucking. And there's a certain limit that happens, and I forgot exactly when or how it happens, but it makes the whole thing crunch in, and then it explodes. Like it makes like a big crunch, which causes enough energy to make an explosion. Does that make sense?
Yeah.
Yes, and I forgot like what the limit was and how it happened, but that's what happens.
Remember, there's some kind of star that's like it's like all protons or something.
Okay.
It's like the most dense. Those are like first generation stars, right? I'm not sure if it's like
only like that's early stars when it's all just like helium, hydrogen, you know, hydrogen, helium.
It's like super dense, and it's like a teaspoon weighs.
Oh, you're thinking what, like neutron stars?
Yeah, neutron stars.
Right. So those are all neutrons, is what they are.
In a sense, because a ball of protons wouldn't really be that stable.
So I could explain to you guys how like the theory about black holes happen if you want.
Do it.
Okay. So you have let's say like you have a fucking white dwarf, imagine, right? Like a weak star, like it's burnt out, but like there's a lot of gravity happening, and it's white dwarfs exist because they're being held up by what's called electron degeneracy pressure, which means like it's just like you have all these electrons and like they're crunched up, and like they just can't quantumly occupy the same state. So it's like it's pushing out and it's making this white dwarf. Does that make sense?
Yeah.
So then The next level is neutron stars. When you have enough mass to collapse beyond that energy limit that you could have electron degeneracy pressure, the electrons and the protons will fuse and make neutrons, right? Because you have the positive and the negative, and you make the neutrons. So now the star is being held up by neutron degeneracy pressure. So you have a lot more. So it's a higher energy to break past that, right? You need a lot more mass than that. So we don't know theoretically of anything that could hold up past neutron degeneracy pressure. We don't know of like the next step. Like, what does it mean to, like, it doesn't make any sense. So like, since there's nothing to stop it, what happens is if there's enough mass and you can get past that energy limit of the pressure pushing out, then it'll collapse in and it'll collapse to an infinitesimal point because there's nothing else. There's nothing to hold it up structurally.
It's just like it's not,
And the thing is, we just don't know of anything between neutron degeneracy pressure and collapsing to an infinitesimal dot. There could be something in between, but we're not sure.
So, like, then how is that doesn't describe all black holes, though, right? Because can you have things like soft black holes versus like?
So that's the edge of my black hole knowledge. I know that there are like supermassive black holes. I know there are different types of black holes. There's the ones that spinning. There's some that don't spin. I don't even know what it means to have a spinning black hole. That's the edge of my knowledge. You know what I mean? So like, yeah, there could be different things. But as far as I understand is it's collapsing to an infinitesimal point. All the mass is there. And then there's different types.
And like, so they observe black holes because like, they nothing can escape a black hole, like not even light, right?
Right.
And
so that's
like, bends around it.
Yeah, light bends around it really crazy, dude. That's like if you look up like Einstein rings and Einstein crosses, you could actually see the crazy lensing effect that happens from gravity because like how the light moves and the gravity you have to remember that gravity shouldn't affect light, right? Because light is weightless. There's no mass to it at all, right? Light is massless.
That's where E equals mc squared.
Right, but light has energy, and like, and an energy is mass. So but like you could think of the gravity is bending the path that light's going through. It's bending the space time. Does that make sense?
Yeah.
Okay. So like,
it's not interacting with light.
It's interacting with the space time. It's like changing the axis instead of changing.
The light's still going straight. The
right.
Still going straight.
Yeah.
But it just changes the perspective.
Yeah. Right. Isn't that crazy?
Straight to the observer is not different than straight that the light's experiencing.
Right. Exactly right.
So the light, no rules are broken. Light's still going in a straight line.
Yeah. Exactly. Is that crazy?
That's awesome,
dude. Fucking
supermassive black holes, like they've been theorized, and now for the first time they just took a crazy picture of them.
Wait, did they actually take a picture of a black hole?
Well, they took a picture of it. I don't know why they chose the dates, but it was like 7 different arrays around the globe. And so they took a picture of it. They haven't processed the data yet. And one of the craziest fucking little detail about this whole thing is that there's so much data, it's too much to transmit online.
Wow. And
so they had to mail hard drives.
Wow.
Like packages of discs, and like the one that's in Antarctica, it's too much. They're like, they can't send it out until October because of the winter or something.
That's crazy.
So yeah, it's going to take like 5 months at least to process the data, and then to even see if it exists right now. I mean, it seems like all the scientists were celebrating and everything. They're pretty confident about it, but you never know what's going to happen. There might be something else. Maybe they discover another state of matter.
Right, exactly. Because there's a lot of crazy things that could happen from here on out, right? Like what we could be discovering from here on out. That could change our view of everything, right? Yeah. Shit's wild. That's a whole other thing. Dark matter and dark energy. It's crazy.
Yeah. Like it's keeping our galaxy together somehow.
Yeah. And like it's crazy. Do you know what? I was watching Neil deGrasse Tyson talk about dark matter, and he's like, I hate the name dark matter. He's like, it would be better called Frank because it would give better information than calling it dark matter. You know what I mean? Because like we don't know if it's even ordinary matter. We don't know if it's matter. So like calling it dark matter, it implies that it's dark and that it's matter, but we don't even know that much about it. You know? We don't even know that much about it. So like that's what we call it, that dark, because we know nothing about it. But like
light doesn't interact with it.
So yeah, well, if light can't interact with it, because we would then very much see dark matter everywhere all the time.
Right.
Because it's a lot of, it's like, what is it? What's dark matter? It's like
transparent matter.
It might not even be matter. Like it's all we know. Okay, this is why we know that dark matter exists, though. Because like if it wouldn't interact with light, then how would we know it's here, right?
Right.
All right. So the reason why we know dark matter exists is based on how galaxies spin.
Yeah, man.
Right? It's based on how galaxies spin, and like, so we could observe how galaxies spin. Like we can look up in the space and we see how the galaxies spin. But we also kind of have an idea of how much mass is in the galaxy based on like all the stars that we could see from the galaxy, right? Does that make sense? So we can kind of assume how much mass would be in the galaxy based on the stars that we see. But so then we do a calculation based on that mass, and we get a very different spinning rate than we actually observe, right? Galaxies. So like, the reason for that discrepancy has to be that either we have a fundamental misunderstanding of gravity, which we're pretty confident about general relativity. We have a lot of evidence for it. The other thing is there could be a lot of matter or something that's affecting gravity in a big way that we just can't see. And that's why dark matter, that's why we know something of dark matter exists.
So as I understand it, the calculation they made that was so different from the observation was they saw that the edge of the galaxy moves at the same velocity as the stars near the center of the galaxy.
Right.
The stars near the center should have been going faster because there would have been more mass there. The gravity would have been stronger. They would have been pulled to the center faster and yanked around. Just like how planets move around the solar system.
Yeah.
Earth moves around the sun faster than Pluto moves around the sun. And so the galaxy moves like it's a windmill. Yeah. Instead of
Yeah, right. And it shouldn't move like a windmill, right? That's the whole thing.
Yeah, but that's how it did it. That wasn't supposed to happen.
Right.
So yeah, if you look at the rates of all the planets going or in our solar system are like the Mercury. Oh, just in the planets, the rates are different. Yeah. So Mercury's going super fast, and then Earth, it takes 3 or 6.
But we're talking about how galaxies rotate, and galaxies don't rotate like solar systems do.
Yeah, it's not. But according to like gravity, Newtonian gravity, Kepler's equations explain planets going around the sun.
Right.
And that's what we're saying. Like we're so freaking confident with that because we have tons of information about how planets move around.
Right.
But when fucking suns move around a black hole and a thing the size of the galaxy, all of a sudden those rules break. Or no, well, he was saying though, so that the Newtonian gravity would explain our planet, but and it wouldn't explain. But but the general relativity explains galaxies, but even it doesn't even line up with the general relativity stuff.
Right, that's the thing. And so like I said, either we don't understand gravity or there's mass towards it has to be towards the outside of it has to be like towards the outside of the galaxy, right, in order to make it spin more like uniformly like we observe it to. Right. It's basically how we have to twist our understanding of reality in order to get us to predict what we're actually seeing.
There's just something there.
That's crazy. That's out of control. I guess that's how you discover new things, though, right?
Yeah.
That's crazy. But, like, that's the thing. We don't know. Like, all we know that is, like, something's weird is happening, and our best explanation for it right now is dark matter. That's our best tentative explanation for it. That's why it has to be a thing.
So
But gravity could just be wrong though too. Like that's a possibility. Like our understanding of gravity is just way off.
Yeah.
That shit's wild.
My college physics teacher, she worked with she got her master's in particle physics and worked at one of the facilities where they just try to detect dark matter.
Oh yeah?
Yeah.
That's pretty sick. Do you know which facility it was? Like where she was?
She's gonna have her master's on her website for Western, so I'll look her up right now. I'll tell you because I'm pretty sure she did it through a university, so it's probably
sick.
I can remember what university she was at, and then from there we could probably make some pretty good guesses as to where that is. I can't imagine there's a ton of dark matter detection facilities.
Yeah, I'm not even sure how many there are.
Yeah, I've never seen pink and purple.
That's cool though.
So
that's really cool. She's doing. If they're doing frontier research though with dark matter, that's crazy.
Yeah, I mean this was when she was like in her 20s.
Oh, okay, but still.
But yeah.
She was on the front lines, like she was there.
She was frontier at the time.
That's crazy. Very cool, man.
Can't even spell her name. I'll have to look her up for the school website.
It's all good. So like, what do you guys think is the coolest thing about science? Like, what made you guys pursue it this far? Like, why are you in grad school doing science? You know what I mean? Does that make sense of a question?
It's cool.
It's cool, right?
Cool, yeah. It's really fun. The type of science I do deals a lot with really pretty pictures and graphics, and so like it's aesthetically pleasing, and that's a part of it for me. I like looking at it. I like the way it looks.
That's cool.
I look at protein structures and electron density maps.
That's out of control. Like you're seeing things that most people don't see. You're looking at through the electron microscope at these protein structures. That's really cool.
Yeah, man. I haven't gotten on the microscope yet. I'm gonna. So it's it's our first year here.
Oh, okay, gotcha.
So we use TEM. We have a few. We have a few SEMs as well. Cryo-EM is just TEM at very cold temperatures.
Okay.
Transmission electron microscopy.
Gotcha.
So I'll get trained on this regular TEM for negative stain.
Okay.
And so what you're picking up is pretty much you put a metal coat in your sample, and that metal coat, you kind of mold over it, and then you shoot that, and the hollowness is what the image you get. And so
that's
if
crazy.
you can Google SEM pictures, they're beautiful. You can get pictures of a fly's eye.
Wow. That's cool.
3 nanometer resolution.
And you can get pictures of, the trichomes and cannabis too.
Yeah,
that's cool.
So TEM can get even smaller than that. So I'll get trained on. Sorry, that's SEM. The TEM for negative stain is kind of like that. We don't use a metal. We use just some. I actually don't know what it is. It's a heavy coat.
Right.
And
Okay.
as the electron passes through it, you can see kind of you're not really interacting with the protein. Interacting with the coat around the protein, and so you can see what the surface of proteins.
Interesting. Okay. Cool.
You can get up to what's like about 20 angstrom resolution.
Wow. 20 angstroms.
2 nanometers.
Now an angstrom is the diameter of hydrogen. Is that an angstrom?
That is correct. Is it the radius of hydrogen or the diameter? I don't know. It's either the radius or the diameter. I can't actually. I want to say it's the diameter. I think.
Okay.
I think that.
That's crazy though. 20 of those though. That's the.
A carbon bond is 1 angstrom.
Okay. Oh, that would be so. The bond itself is an angstrom long.
Oh, about 1.5 angstrom, I should say. Yeah.
Okay, so I would think it'd be the diameter then, right?
An angstrom is 1 × 10⁻⁻10 meters.
Okay.
So its relation to an atom it's not going to be a perfect.
Oh, okay.
Always about, because the angstrom is defined by the meter and not defined by
where did angstrom come from?
Yeah, so it's a Swedish. I'm just looking up here. It's the Swedish physicist Anders Jonas Angstrom, 1814 to 1874. It's a letter of the Swedish alphabet, but so this guy, he was a pioneer in the field of spectroscopy, which is using light to analyze things. And this is back in the day. I mean, this is the scientists that I have like a high regard for scientists back then. I mean, they it's like they're doing everything from scratch. I know it's just
pioneered the field.
Yeah, dude.
It's amazing what they did back
then. It is amazing. Back then, there was no difference between a theoretical scientist and an experimental scientist. It was the same. Like, you had to be both.
If you weren't even called scientists. Like before biology, there was naturalism.
Oh, interesting. And how they define naturalism compared to like science?
Naturalism was the science of nature, kind of.
Okay.
So kind of biology.
What spawned biology?
Like, naturalism is like the precursor to biology.
Okay.
Like, Darwin existed before the term biology was commonly used.
Oh, interesting. That's crazy. I had no idea.
Darwin was a naturalist. That's how he identified himself.
Interesting. A naturalist, huh?
I think they call themselves scientists.
I know back in Greek times, like scientists were
philosophers.
Natural philosophers.
Yeah, well, so it was a lot more common for people to be to just kind of do everything. I mean, like it was very common for like.
It was mostly just thinking.
Yeah, I mean, like astronomy and mathematicians and chemists, and you look up like these old ancient thinkers, like different sultans and like the Greeks and these guys, like, and they just did everything. You know what I mean?
Right. Yeah, dude, like those old guys that you look up, like Pascal or whatever, was a mathematician, a philosopher, a scientist. Like he did like all that shit. That's crazy.
And like,
they're pretty indistinguishable.
I guess you're right. You're just like That's weird. Yeah, I guess they did because they didn't have names for it. Like it seemed like they were doing one thing, but they were really doing a lot of things.
And that's if that's not evidence for like the birth of an age.
Yeah.
We all do this thing where we think a lot, and we know a lot more than other people, but we don't know what to call it. This is so new. How is it?
Dude.
Like, you want to drink the water, and I want to know what is water.
What? Yeah, what is that? What is that water? That's crazy.
A beautiful Isaac Asimov quote.
Yeah.
So I believe it's, I'm sorry, Isaac Asimov paraphrase.
Okay.
I don't quote it if I don't know the quote.
I love it.
Into the praise of science is not eureka. It is, that's interesting.
I like that. I saw that before. That's really cool, man. Exactly right, though, because like that's not like science doesn't happen when we're like, oh shit. It's like, oh, that's kind of a little weird thing. Like when we discovered penicillin, right?
You know, just off of fungus.
Yeah, he that could have easily just been like, oh, this is a shitty experiment, throw everything out. But he was like, oh, why are they dying in that ring shape or whatever? And then he discovered penicillin, and it was a big deal. Like antibiotics, that was the beginning of antibiotics.
Man, that's crazy. We just think we didn't invent antibiotics. We just
dude,
hijacked.
Things would be real different if we didn't have antibiotics. Things would be real different. And I think like we forgot what it was like before antibiotics. You know what I mean? Because like right now there's a big problem that
actually we're about to have kind of a painful reminder.
Yeah, that's the problem, dude. Like we're giving out too many antibiotics, and like we know what's gonna happen when we do that. Like we're giving out too many, and everyone's like, stop doing it. But like we don't care. We're just like they keep giving out the antibiotics, and then we're gonna have the resistant bacteria, and we're in big trouble.
Yeah, man. Well, we just saw this talk on Friday about this seminar, and he was talking about antibiotic, and so this is a nanoscience guy, and so a lot of with nanoscience, I kind of like didn't get it. I was like, what's up with these nanoparticles? Why are they so special? Like, particles of a certain size of a metal. In this case, he was working with gold, and they use all sorts of stuff, but gold is kind of beneficial because it was for in the body. Gold is very toxic, right? And so you coat particles with like a substrate. It's kind of like the same thing with soap. The way soap cleans is the fatty part or the fatty chain, and then the end of it is like a water soluble part.
Right.
It grabs the fatty part grabs onto the shit, and then
the shit it's cleaning.
Right, and then it goes away with the water, right? And so these things, they surround the particle, using them to like deliver drugs right into the cell. So normally, what happens with the drug is it's designed, or there's a lot of cases, but like drugs like cannabis or whatever, THC, whatever you want, hit like receptors on the outside and they cause a response on the inside, right? Yeah, they don't necessarily go inside the cell, right?
Gotcha.
Not always. And so this case, and so I don't know exactly how antibiotics work, but they don't like. I know how antibiotics work. Yeah, how do they work? All right. So antibiotics have to. So a cell is a living thing. A cell needs to be alive. There are certain things that a cell has to do to maintain its viability to be alive. You have to be able to make proteins.
Right.
You have to copy your DNA. You can make proteins. You can't do shit. You can't copy your DNA. You can't multiply.
Right. That's a big problem both ways.
Yeah. So now, lucky for us, even though every living thing has ribosomes. And
that's crazy. Everything.
Yes, that's how fundamental ribosomes are. Ribosomes are the giant, even nuclear proteins. Viruses use ribosomes. We don't know if viruses are alive. Right.
That's a whole other thing.
That's actually a huge contentious debate. Right. Are viruses alive? But is that one of the big distinguishing factors? Because why it's like viruses, they multiply, but they can't multiply without a host.
Right. And they don't have ribosomes. They're not making proteins either, viruses, right?
Yeah, it's like Zika virus. It's literally it's a capsule of proteins, and like they don't even have a membrane. They don't have a fatty membrane. It's also viruses are just capsules of proteins with RNA inside.
That's crazy. Yeah, right.
And they dock onto a cell, and like the proteins go like open up the cell and just like dump their genetic information into the cell. And then the cell's like, oh, hey, genetic information. I can make proteins out of that.
Dude, I'm playing like an action movie in my head right now.
So antibiotics still work on viruses. That's why antibiotics don't work on viruses, because antibiotics use you, whereas viruses use you. Antibiotics kill living things. If we have an antibiotic for a virus, we just have to kill yourselves.
Right.
So how antibiotics work? Let's say the ribosome, you need to make proteins. So there are these antibiotics. There's one called I'm blanking on the names.
Antibiotic? Anything acillin.
Not all antibiotics. All antibiotics bind to some machinery.
Right.
I have like a polymerase, which is for DNA replication.
Okay.
Or the ribosome. I'm forgetting the names. I forget which one penicillin binds to.
Oh, okay.
I'm forgetting if they bind to a replication machinery or translation machinery.
Gotcha. Okay. Honestly, dude, you can literally say whatever you want. I'll be like, oh yeah, that sounds bad. That sounds right. I appreciate that you're honest, though. I really do appreciate it.
Lost my own jargon. Information has to go into a giant ball.
Right.
And that ball spits out proteins that do shit. If you put a plug in that ball and the ball can't turn,
right,
all can make proteins.
Yeah.
Bacterial balls are different than our ribosomal balls. So if we throw in an antibiotic, it will go into our cells, but it won't bind to anything because it's not used. It doesn't know what to bind to.
Right.
But if we go to the bacterial cell, there's the ribosome ball.
It's just right there, and it binds right to it.
And it kills it.
That's awesome.
So that's how antibiotics work. And
that was the best. Wait, that was the best explanation for antibiotics I've ever heard. That's awesome. The different balls, I'm all about it.
And so, like the cells in the bacteria can evolve a resistance to that. Right?
Yeah, right.
but it stops the antibiotic from binding to the ball.
It's like the balls that it doesn't bind to are going to be selected for now because they're going to stay alive.
And that's Darwinian evolution. Yeah.
Right.
That's like
they're evolving. They're evolving to deal with our bullshit, and they're doing it well.
Because they're like, we're just trying to live.
Yeah, exactly.
Trying to get by.
Ah, man.
It's targeting a spot that like they can evolve. You know what I mean? But like, there's drugs. There's other substances that can kill the bacteria just by like just destroying the walls of the bacteria, just like destroying it. You know what I mean? Just
right.
Like, but you know, these things are also toxic for your cells because they're made up of the same cells.
That's the problem because we want to kill the bad cells, not the good cells. We're just a pile of cells trying to deal with which ones are good or not. That's really all we're doing.
This guy with this guy with the nanoparticles, he can deliver compounds that have been known to be antibacterial. Like he was mentioning peppermint oil,
okay,
and thyme oil, and he can use nanoparticles to deliver those things right into the cell.
Okay,
and kill bacteria. All right.
So that's crazy. So like the oils that have been around forever, like these peppermint oils or whatever, they just have to deliver them the right way with these nanoparticles, and then we have a whole new antibiotic that's better than the function we have now.
Dude, how do you think peppermint survived all this time?
I guess you're right. I read that's why caffeine became a thing, because caffeine kills the bugs that eat the thing, right? Like it kills the bugs that eat the beans. So, but we're like, oh shit, caffeine's awesome.
Well, no, cannabis. It's not well understood. Cannabis is a thing where there's like a few different theories. It's probably what a product of the interaction of all of them is. So like the trichome, the cannabinoids are present in all the tissues at low concentrations, just like 0.31%, something like that.
Mm-hmm.
You know where it all is. It's in the bud, right? It's in the flower. It's depending on like how much, what kind of different weed, weed with the seeds in it,
right.
Like if you smoke pot with seeds in it, like it's kind of not common so much these days, right?
Right.
Plus the seedless kind is better anyway. But so you grow the.
But you can smoke the seeds. It's just they don't do nothing for you. It's just like in the way, right?
So you have to pick them out.
Seeds are just genetic information. That's just DNA most.
But it's like a whole. It's a fucking seed.
That's what I'm saying. There's no THC in it. Oh yeah. It's literally like a seed is hardly a living thing. It's pretty much just genetic information. Like,
right.
And there's also there's food for the seed to live. That's why they're like yeah. And so the trichomes grow right on the outside of the tissue.
Okay.
And so not all, you have this THC and it's like antibacterial, and the terpenes are antibacterial and all this kind of crazy stuff. But the way they're arranged, they're like these little lenses, and they grow in pretty sunny places. And what's interesting is they have a different distribution of cannabinoids in different altitudes. So you have THC.
That's weird.
In the equatorial region, you have the stuff that actually gets you high. That's
right.
But higher up in Russia, you just have CBD pot that doesn't get you high.
Well, why do you think it's correlated, the altitude and the THC?
It's they say it could be from radiation.
Really?
The radiation they receive is different, right? It's different, less sun basically, and
okay.
So that explains differentiation of species. But I'm talking about how the psychotropic effects really blossom.
Okay.
So if you imagine you have 3 plants growing, 2 of them you eat and nothing happens to you, 1 you eat and you get really stoned. Yeah. Let's say just an animal they're just gathering food.
Right.
You're going to eat one plant, this is great. You eat another plant, you get really stoned. You're freaked out.
Yeah.
You're paranoid someone's going to kill you. You don't know what's happening. You're just like, I was just trying to eat. Now everything's different.
Oh, interesting.
Those ones.
Yeah, but why would almost the same plant have a different cannabinoid that doesn't get you high?
No, I mean it's.
Now wait. Do you think that for a plant to be psychoactive, do you think that was selected for or against?
I think it was select. It was selected for its survival. I mean, what do you mean by selected for?
Well, okay, well, it's obviously here, so it was selected for. I mean, like, how about this? Do you think it survived because we avoided it? Like, we didn't want to feel that way, or that we seeked it out actively and somehow helped it in its reproductive cycle?
I think since its discovery, that happened 100%.
Okay.
I'm saying before humans discovered it,
I
think it started like, I don't know, some like creatures didn't like the way it felt.
Yeah. Well, it's a very sticky substance. So like a bird might have like a different reaction to it. So like think of like berries, like the berries that grow kind of in the wild that are like really bitter.
Yeah.
The bitterness that it causes is from tannins, right?
Okay. Oh, like in wine when they talk about the tannins.
Yeah. and they're bitter to us, but birds don't taste it at all.
Really?
And so it's kind of,
and we don't like bitter. We go away from bitter, right?
Yeah, so we don't need it. And so like the way we distribute seeds is when we eat them, we shit them out. But like around where we are, like however hunter-gatherer societies, like with the birds, they fly around. And so like however the natural selection works, like the plant preferred to have
right
birds
eat the seeds, so it craps. And dude, that's perfect because it eats the seeds, and like fertilizer is crap, right? So you're just like, you're getting them fertilized and you're spreading them everywhere.
Yeah,
that's brilliant. That's the smartest thing ever.
And so like it's not understood with pot, but like another kind of little thing little twist of the story is that THC, it has like an ultraviolet expression to it, right?
Really?
So birds see an ultraviolet too.
Oh, interesting.
So like, flower
what?
Yeah,
that's amazing.
There are flower petals that look like all one color to us, but birds see like other patterns to it.
So if you held a black light to those flowers, can we see that stuff? Is that how that works?
It's possible. Like they take a picture of it with an infrared or with like an ultraviolet camera.
Okay.
Infrared, they see
the ultraviolet through the camera. You know what's weird? You know what's really weird though when you think about it is like when you take a picture with the ultraviolet camera, like the camera's detecting the ultraviolet and showing it to you, but it's still showing you on the display in color. You know what I mean? We're not seeing ultraviolet. We see that something's there as ultraviolet, right? But we're just seeing.
It's just measuring intensity.
Yeah, right.
From 0 to 1, and I can detect these wavelengths.
That's crazy.
And then it's just from a white to black, and then you can colorize it and say blue is cold, red is hot.
right. But that's crazy.
You assign intensity to each shade of blue and red,
right?
And then that's how you get these really beautiful different. Because you can kind of graph from the ultraviolet spectrum to the color spectrum. You can say I want to represent this level of ultraviolet with blue, this with red, and that's how we see all the different colors because they're just assigning different intensities to different colors. That's why we're grafting ultraviolet light
into the visible
spectrum. So
right.
Yeah,
that's crazy. That's out of control. So we know it's there. We just don't know what color it is.
Yeah, that's the near odds are good. That's why we take it.
Dude, yeah.
I think I understand it a little better now. That's just a transformation.
That's awesome.
Futurama with Dr. Farnsworth is like, I think we're going to have to use math.
That's awesome. Yo, wait. But math is crazy, though.
Yeah.
That it works so well.
Can I show you something?
Yeah, of course. Is that a tattoo? What does it say?
It's a tattoo.
I can't. Oh, is that's kilogram meters per second squared?
Yeah. Okay.
Plus.
He'll do it straight.
So we're talking newtons, right?
Yeah.
Plus the limit as n goes to infinity of 1 plus 1 over n to the n. Is that that converges to something, doesn't it?
Yeah.
So if I go, that's going to converge. Is that going to converge to fucking? What I don't know. What does it converge to?
No, you were close. You were close. You know, say it.
Infinity? Infinity?
Not infinity.
It doesn't go to infinity.
Oh. It's probably the second most famous number.
Is it one? It goes to 2? Maybe 3?
No.
That's famous.
We'll go back to it.
All right.
Close to 2.
Yeah, it's between 2 and 3.
Okay. Oh, is it E? Is that E?
Yeah, it's E.
Oh, shit. Okay. Okay.
All right. That next one. This is the one I'm most proud of.
Okay. That's okay. The natural log of this is a thermodynamics thing?
Yes.
Okay. Fuck. Is that entropy?
Entropy on top. Yeah, it's entropy times Avogadro's number.
Okay.
Yeah.
Over the natural log of work, right?
Degenerate microstates.
Degenerate. Okay, so is this shit? Isn't degenerative microstates entropy?
Yeah. So I mean, what's the formula for entropy?
I guess is that it?
It's S equals Boltzmann constant times the natural log of microstates.
Oh, okay. Oh, so is this rearranging the?
Yeah.
Okay.
So what's Avogadro's number times the Boltzmann constant?
Avogadro. So that would be that. That's a particular. Fucking.
Avogadro's number is the number of things in a mole.
Right.
It's units of per mole.
Okay.
And so Avogadro's number times the Boltzmann constant. Boltzmann constant is the energy factor.
Uh-huh.
So Avogadro's number times the Boltzmann constant gives you kilograms, meters, joules per mole Kelvin.
Joules per mole Kelvin.
Joules. The units
right.
That breaks down to.
Joules per mole Kelvin. Dude. Oh, man. Thermodynamics is hitting me like a fucking like that. Like a Vietnam flashback, dude.
It's the ideal gas constant. Yeah. R.
Oh, that's the Rydberg constant?
Yeah. Oh, no, not Rydberg. Rydberg is the constant for electrons going to different energy levels in hydrogen.
Oh, right.
This is the ideal gas constant R.
Oh, okay. Gotcha.
So, and then this last one, dude, you're doing so well.
Is that that's fucking the magnitude of 3-dimensional?
You're the only person who's used the correct jargon.
Yeah, all right, good. That's the magnitude.
It's actually simpler meaning than that. It's the magnitude. What's another word for magnitude? In terms of position. In terms of letters. In
terms of position, magnitude.
Yeah. What's a magnitude from this point to that point?
A distance.
What's that called? It's distance. So
okay.
What's that letter?
D. Okay, so we're spelling something here. Okay.
So what's the spell?
N-E fucking what was it? R. N-E-R-D. Nerd?
Yeah.
Dude. Oh man. That was some puzzle, dude, that you put me through. Yo, nerd, okay, I like you. That's awesome.
You're the that's amazing. Yeah. I got one of them, I think. I forgot. I think I got E.
You got E.
That was it though. I saw someone else got it. They got something else. But
that's awesome though, dude. That's so cool. That's such a cool code for nerd. That's awesome.
Yeah.
Wait, I saw a tattoo on your other arm though. What's on your other arm? What is that?
All right. So I got my undergraduate degree in biochemistry.
Okay. So
I'm a protein guy. I worked in a protein chemistry lab for 2 years.
Okay.
So proteins are made up of amino acids.
Right.
And amino acids, there's 20 of them.
Yeah.
All right. So there's that first one there is histidine.
Histidine. Alanine.
Aspartic acid.
Okay.
And then it repeats aspartic acid, alanine, aspartic acid.
Is that the particular protein you studied or something?
Not a protein I studied, but since amino acids, proteins have large numbers of them, so you have to give letters to them so you can read sequences.
Oh, is this gonna spell something again?
It also spells something.
All right, cool. So
it spells HADDAD, which is my last name.
Oh, cool. Yo. All right, that's awesome. Based on so you made your protein, your last namesake protein.
Yeah, I spelled my last name of protein. proteins.
That's sick. That's very
cool.
cool.
And amino acids. So this I got this one first, and I got this one a year later. Like I got this
Nice.
one.
That's very cool. So Jay, where's your tattoos? Huh? How much do you love science?
I don't have any tattoos.
No tattoos, me neither. It's cool.
Yeah.
I was thinking though that if I was to get a tattoo, it would be like I was thinking doing force is the rate of change of momentum. You know what I mean? Because everyone says force is F equals ma, but it's really the rate of change of momentum. It's not really ma. You know, like if you take the derivative of momentum, you end up with like you end up with ma, but there's another term there. It's like it's actually like so ma is so like all right, momentum's mv, right?
Yeah.
You take the derivative of mv, you end up with ma, but it's a product rule. So like, what if mass is changing with time? So you have to take the derivative of mass too. So it's m times a plus the time rate of change of mass times v. That's actually what force is defined as. There's a term there, but the thing is, usually mass doesn't change. So like, imagine like when you put a force on something, the mass usually stays constant and just goes through. But what if it's like a rocket or something that's like the mass is changing as you go? You're burning fuel.
Wait. Force is the derivative of potential energy.
Yeah, that's that too. It's also the time rate of change of momentum too.
Oh God! Physics, you asshole.
Dude, but like the math is crazy. The math is crazy. Wait, it's not the derivative of potential energy, isn't it? The integral of potential energy?
Potential energy is the integral.
Fuck, I forgot which way it went.
I wrote a work calculator.
Oh, okay.
Work is the type of energy.
Okay.
For a simulation, outputs a force constant, or just a force, like piconewtons.
Gotcha.
I can bring that over position.
Okay.
Get force at a distance, which gives you kilograms meters squared per second squared.
Okay, that makes sense.
So work is a unit of energy.
Right.
Work is related to potential energy when you're looking. So work is the derivative. Sorry, force is the derivative of potential energy.
Okay, right. Dude, how you just walked me through that was awesome. That was really good. I know exactly what you mean.
If you have, so think about the different ways of looking at the definition.
Yeah.
If you have a car that's, let's say you're crossing the street and there's a car heading towards you.
Uh-huh.
It's hitting the brakes and it's decelerating.
Mm-hmm.
Okay. Hits you with force, right?
Right.
But it's decelerating. But if it's mass times acceleration, you have a negative acceleration.
Well, wait. So the car itself is decelerating, but still hits you. That's momentum. That's.
So momentum,
yeah. But like.
So if you look at it like a momentum thing.
Yeah.
But I think that's also that's
force is how much momentum changes in time, but I guess force is also how much energy changes in time. No, in position. How much energy changes in position, right?
Yeah,
that's weird. Wait, hold on.
Time definitions of force and position definitions of force. That's interesting.
That's what? Hold on.
Well, that's what you're telling me, right?
Oh boy.
Momentum implies some position because it's velocity and it's changing position.
Right.
Okay, so
momentum is mass times velocity.
Mass times velocity is momentum. So fuck, man. Force is weird. I gotta think about force a little deeper now. Like, dude, you know what's weird though? Hold on. I learned this. I learned this in college, and I was like, yeah, fine. You know, force is energy but over position, and yeah, fine. It's momentum over time, whatever. Like, I just learned that, and I put on the test, and I kept going. But like, that's a big deal, isn't it? That's two different things. It's like defined as, right?
Wow,
that's weird.
So what's your definition of force?
I don't know, man.
I mean, like, what's the one that you want to get attention to?
Okay, so that was where we all started, right? It's the time rate of change of momentum.
So
it would be F with a little arrow on top is equal to dp with a little arrow over dt.
Okay. Oh, okay. Yeah. P being position or the momentum.
P being momentum. Yeah.
So you can use
the dp differential equation.
John, you have to use dp over dt.
Oh man.
You can't say what I really mean because it's copyrighted, right?
Wait, is it copyrighted?
I'm confused. You have to use the dp over dt.
dp over dt?
There's a sex joke in there.
Is there?
He says force is dp over
the force, like the force is copyrighted. Okay, like the Star Wars force is that where that was going from?
Yeah. Okay.
Okay.
I didn't get that.
Gotcha. Yeah, I'll be careful with the copyright.
Dude.
All right, guys, I'm ripped.
I'm pretty high. You got some fucking tired.
Yeah. Good. I'm glad you guys had a good time.